All right. Hello, my name is Miguel Torres Gonzalez. Let me check this recording. Yep, good. Yep, my name is Miguel Torres Gonzalez. I am part of Oz-based class for Fundamentals of Aerodynamics. This is Project 1, where we will be simulating the NACA 4424 here in ANSYS. So, let's get started. First thing I gotta do is fluid flow, ANSYS Fluent. We're gonna do a 2D sim. In geometry, it's opening up discovery again. Yeah, this is not right. I accidentally opened it. Uh, yeah, my mouse must have double clicked and just opened up discovery. Did not mean to do that. All right, let's close that. Still starting. Anyways, first thing we're gonna do is make this into a 2D geometry, which I'm not gonna use discovery. Discovery is good and everything. This is great. Um, However, it does use quite a bit of resources, and I'd say it's really only viable for it's better viable for 3D stuff. For 2D stuff, you could just run it with Design Modeler, which is a lot faster and cheaper to run. But you could also run it on a CAD interface, like how I used to before. But yeah, right now we'll just run it on Design Modeler, so it'll be very easy and quick to run. Okay. Yep. Really quick, as you can see. Now, Now that we're here, we're gonna have to import our geometry. To do that, we're gonna do concept 3D curve, and in the 3D curve, we're gonna need our coordinate file. To get our coordinate file, I'm gonna open up Airfoil tools right here. Then we look up our airfoil. I have many here saved. I'm gonna go NACA 4424. This guy right here. Send to airfoil plotter, and then we're gonna do 1000 millimeters, which is 1 meter chord. Okay. Be sure to click plot. Now to click plot, then it saves everything, and then you could click a CSV file of coordinates. I've done this many times. And now that we're here, what we could do here is delete everything that's unnecessary. That includes the camber line and chord line. Okay. Now that we're here, you got to shift it up to this corner here. And we're gonna need these headers, these tabs here. Group, point, X, Y, Z. Okay. And group, all of it will be 1. So just double click that. And point, you just go counting from 1 to 2 all the way down. And then for Z, just click 0 since this would just be a 2D curve. And now ANSYS will give you an error if you just import it straight up like this, because you have 2 points that are the exact same coordinates. You just delete these, and to close the curve at the point, the last one, you just type 0, back to point 0, and this will close the curve. Now we've done that, we do save as, and I'll make a text file for this. I've done this several times, as you can see. And tab delimited, NACA 4424. Yep, there you go. I'll name this ANSYS here. This is all lowercase up there. And there you go. Save it. And then we go back to ANSYS. Here in ANSYS, keep in mind where our units is in millimeters, so we go to millimeters. And then in the corner file, you just look it up. I have several files here, as you can see, but we're gonna go here in downloads, and this is the exact same one that I've made. It works. good. You could press F7 to zoom to fit. There you go. And now we make a surface from edges. Click on the edge, apply, generate. And there you go. Next thing after that, we have to make our domain. Go to sketch. And in sketch, you do arc by center. And we're going to make two of them. All right. One smaller one and one larger one. Right here, right here. Okay. Now that is done, just create lines going straight up. Here, here, here. And you're just essentially going to just close these. Corner. Right here. Modify. And then corner. Right here. There you go. Now you can see that we're going to have a shape like this. We're going to have an inner one and an outer bullet. So this outer shape right here is just the entire size of the domain. And then this inner one will be our refinement region. Go here to dimensions, and we just do some general dimensions. Radius here, horizontal line there, radius here, horizontal dimension there. Now R1, we're going to specify this as 7.5, so it's 15 meters in diameter. Then H2 here will be 15. Then we're going to do R3, this will be 2. And H4, this will be 6. Right here, just like that. Alright, now we go back to modeling, find the sketch, and then we're going to do lines from sketches. Click on the sketch and apply. Now that we have that, what we're going to do is create a surface from edges again, and you're just going to click all the outer edges. Right here, apply, generate, and there you go. Next thing we got to do is a face split. Click on the face here, and then the tool geometry, this will be, make sure the filter is like correct, and click the inner domain right here and apply right there. And then next thing we got to do is a boolean subtract. Target bodies the outside, two bodies will be the inside. No, two bodies will be the inside right here, that airfoil. And then you press F5 to generate, and there you go. Now hide these line bodies. These will cause problems to your mesh, so you want to keep them hidden. The sketch won't show up in the mesh really, but I'll just hide it right there. And make sure it's split, so you can see if I select the face filter, you can see there's two different faces. That's what we want. And yeah, now we got to close it. Close Design Modeler, and we'll go back to Workbench. Okay, I'm sure that's 2D. That's good. Now we go to Mesh. Okay. All right. Now here in the mesh, first thing I'm gonna do is name our boundaries. So I'm gonna name all the edges here, the outer ones. I'm gonna name it inlet. This one here will be our outlet, and then the airfoil will be our airfoil. NACA 4424. There you go. Yep, that looks good. Make sure they're all correct. You don't accidentally click a face. And yeah, now we could start with meshing. I'll do a sizing refinement on my airfoil here. Click apply right here. And number of divisions, this will be an edge sizing, so here we go. I'll leave this alone, but number of divisions, this I'll set to 500. There you go. New, and I'll make another sizing, the interface, and element size, I'll go 0.0. I'll do 0.05. right there. Looks good. I mean, I could go a little smaller, 0. No, I'll keep it 0.05. And then now next thing you gotta do is inflation. So in geometry, hit Control A to select all of it. There you go. And then in the geometry selection in the boundary will be the airfoil. There we go. Now for our boundary layer conditions, our boundary layer mesh, the options will be first layer transition, 1E -5, and maximum layers, I'll set this to 30. There we go. Now that's done. Now we could do a method. Hit Control A again, apply, and this will be triangles right here. Now we're not going to start meshing yet. I'm going to mess with this. So we're going to go 0.0125 right there. And then in advance, this is important. In advance, I'll set it to 32 because I have that many cores. So you see right here, I have a pretty powerful computer. But you know, this depends on your computer, so you know that'll be up to you. Now we're ready to run. So I'll click generate. There you go. Looks good. You know, of course, you could make the inside finer if you want, but I decided to keep it 0.05 because we're going to be running this simulation several times at several angles of attack. So anytime we save on one simulation, you know, it accumulates. So yeah, we're going to close here. This looks all good. There you go. And then update our mesh. All right. Now we could go to setup. I'll use double precision, and then in here, I'm not going to run all 32 because this will make my computer run extremely hot. So I'll run 24. With meshing it was fine because it was pretty quick. But for here, in the setup, this will be sustained over a long period of time. Maybe sometimes it could be an hour, although for me it would be like 15 minutes. But depending on your case, if it finishes in an hour, then yeah, good luck. So this will sustain your course. So click start. All right, now that we're here, I'll just give it a minute to fully load up. But one thing to note is that when running a simulation where the situation can create a lot of wake, especially at high angles of attack, such as like 15 degrees, what can happen is that your physics model, the selection of a physics model becomes more and more important, especially with modeling that turbulence, with the turbulence wake. So K omega SST is pretty versatile. I know some people that got this to work with K omega SST. However, every single time I use K omega SST, it would always predict separation too early. So in that case, I just use transition SST, which is kind of a variant of it. Um, so yeah, I'll use transition SST. The specific you know, choosing your physics model is kind of something that's at a graduate level topic, and this kind of it gets pretty advanced. So we're not gonna go too far into this, but I will just say that transition SST will works pretty well, at least for me. So click OK, and now we have that. According to our problem statement, the density will be 1.2, and then viscosity will be 1.8. Of course, this depends on your problem, so do keep that in mind. Now, of course, make sure it's all good. Everything's all great. Now, boundary conditions, inlet. Most people, what they do is that if they go here in inlet, let's say, put a components, and then they'll make a new parameter right here. However, I have a better way of doing that, is that instead of having to individually calculate each velocity component, and this is something I came up myself, I found out by myself, just do named expressions, and then set one for degrees. I'll do -3, so we're going to start from -3 to 15, and set this as an input parameter. And there you go. And I'll do the same thing with velocity magnitude. 15 meters per second squared. We're going to go 15 meters per second because our target Reynolds number is 1 million. So this will 15 meters per second will get us there. Input. And I'll set that as an input parameter just in case if, let's say, I need to change my Reynolds number. I can do that on the fly. It's pretty easy, so why not? And I'll do ux right here. Ux will be u infinity times cosine alpha right here. And this, you just leave it alone. Just press OK. There you go. And a new one for ui. And then this one will be u infinity times no, not u. Sine alpha. There you go. And then here you can manage and check your variables. Always check the units. For angle of attack, they'll always say radians instead of degrees. That's because ANSYS would always convert from degrees to radians. So do keep that in mind. This can be changed like in the workbench once we finish here in Fluent. But it is still -3 degrees. Just keep that in mind that when it says dimension radians, it just means that it's just converting it to radians because ANSYS just likes radians. Here, meters per second, good. And it is important, make sure all this is meters per second and that your formula is correct. Right here, and there you go. Now if we go to inlet, components, and I'll do ux and then uy. To get a better chance to not predict separation too early, what I'll do is do intensity and length scale. 0.5 and 0.07 right here. For a chord of 1, this is like 0.07 of your chord, so do keep that in mind. But yeah, there you go. And now that that's done, we go to reference values. And then in here, it should be inlet and reference zone, your body. Make sure these values are correct because if they're not, then your coefficients will be way off. Alright. Name expressions are there. So it looks good. Now we do our report definitions. And I'll do some for both force and lift. The project you only require coefficients, but I just do forces just to see if my coefficients are correct. That's why I would use lift forces just to see if my coefficients just look right. I could just calculate myself. So lift coefficient right here. Output parameter. This looks good. Make sure your force vector is good. And then here you could press OK. Force, drag, and this will be drag coefficient. And the NACA. And it's important to click create output parameter because else you will not see your results when you're simulating all the different angles of attack. So now I'll just do lift here. Here you go. And drag. Drag force. Print to console. Good. There you go. This all looks great. Okay, close it. And then now, monitors, I'll leave this default because we're going to be running many simulations, so this will run quicker. I'll leave it like that, but if you wanted more detail, you could mess with that. And now we'll go to initialization. In here, I'll increase the number of iterations to 20 because it will take a little bit more iterations than usual, but it's fine. There you go. Initialization finished. Now we run our calculation. I'll do like 300 iterations, but of course numbers can vary depending on how much detail you want. Here we go. There you go. Residuals look fine. They look really good. Pretty healthy residuals. Now we could check our mesh. This is one way to check your mesh. It's a good parameter to see if your mesh is good. Is turbulence and then y plus. I always do this just to check if my mesh is capturing that boundary layer really well. And there you go. As you can see, the max value is 0.377. That is good. I always target a y plus under 1. If it's greater than 1, like if it's like less than 4, maybe you can get away with it, like maybe around 3. But any greater than that, then your results will be way off, and you should not trust your simulation. But yeah, but y plus of like under 1 is great, it's excellent. So yeah, this is finished, and now we could close our simulation. Close Fluent. Okay, now we're here in the workbench. To run this simulation on many angles of attack, you're gonna have to go to parameter set, which is right here. Okay. Now, as I mentioned before, ANSYS likes to convert to radians because it much rather prefer radians. But you could change it to degree, and as you can see, it's still at -3 degrees. Using named expressions is much better because you're less likely to make a mistake. So all I have to do is just go to the angles I want. In this case, I'll do increments of 3 for my project. Right here. So -3, 0, 3, 6, 9, 12, 15, 18, 21. And now we could just run it all right here. Yep. And then this, for me, this will take like about 15, 20 minutes, depending. So, yeah. Maybe even 30 sometimes. I think it will be 30 since I'm using a little less cores, but we'll see. Okay, we're finished. That ended up really fast. That was like around 8 minutes, I'd say. Give or take, around there, 10 minutes. I wasn't really keeping track, but that was pretty quick. Now we have all these values here. Keep in mind that ANSYS, when we were calculating our lift, our coefficients and forces, keep in mind they're the directions in the unit vector of the global coordinate system. Meaning, i.e., that the lift and drag forces are normal and axial to the airfoil, not to the direction of flow. So to deal with that, what I have to do is open up an Excel file. Right here, I have one right here, and keep it right here. In here, you're gonna have to upload your data. You could just copy and paste it, and I'll just name this AOA, and then velocity. Then this right here will be CL CD L D. There we go. And then I'll just create a merge in here saying that this is fluent right here. And in here I'll do the actual CL CD L D. There you go. And then now in here, let me pull up the right here. I have it here, force balance coordinates. There you go. So this is a NASA paper on this. This is actually pretty simple to do. For lift right here, keep in mind that lift, this works for both the coefficients and forces because the only difference is that with the coefficients you have you're dividing by your dynamic pressure. So and also times the chord, but in this case our chord's 1 meter and our dynamic pressure is, well, constant. So free stream dynamic pressure specify. But yeah, here we're gonna do is our lift force. So our CL will be equal to our CL from fluent times cosine, and then here I'm gonna do radians because Excel only does trig it through radians. And then in here I'll do AOA, and then minus our drag coefficient times sine angle attack. Bam. There is a typo. Oh yes, that's why I forgot a parentheses. Yeah, no. Radians right here. There we go. Yep, let me just make sure it's correct. And then drag it all the way down. There you go. And we do basically the same for CD. The only difference is that for our formula, what we're going to do is CL times sine angle of attack, AOA. And then we're going to do, no, radians. I keep forgetting that. Radians right here. And then plus our drag coefficient times cosine radians angle attack. Oh. Yeah, I made a typo again. Here, this all looks good. Yep, all looks good. You just drag it all the way down. And you basically do the same for lift and drag forces. Although I will just copy and paste them right here. Control C, Control V, and in here instead of F5, what we're gonna do is our drag and our lift. There we go. Yeah. The same thing we did here. Copy, paste. F5 will be our drag. Here. Just gotta make sure that these are all correct. Yep, 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 yep. All looks good. Okay. And this guy here will be our actual results. And there we go. Now, of course, we can make tables. I mean charts for this. Line integral here. Add x values. I'll just do simple graph right here. Use these ones here and add. And you can see our data does follow the thin airfoil theory up until about like 12 degrees. 15 it reaches max, and then it'll start to drop. This is realistic to the actual airfoil. So if we look up the data for our airfoil right here, NACA 4424, airfoil details, and Reynolds number is 1 million. Now, I wouldn't really trust the I don't think I'd really trust this data too much since it doesn't really follow the thin airfoil theory. But rather, there's some images we could look over from NACA themselves back in the 60s and 50s. There were some images, yeah, right here. And as you can see, angle of attack in degrees. This is moment coefficient, so this is not right. Section lift right here. This is correct. Yeah, section lift, angle of attack. We see that around like 16 degrees, we see it starts to drop. This does follow pretty much similar to our graph right here. Keep in mind our graph is wider. But yeah, it does look correct. If we look at 0, we get like around like 0.3-ish, close to 0.4. And here it's the same thing, 0.35. So yes, it's safe to say that our simulation is correct. I mean, well, accurate, so to say. So this is CL over CL over alpha right here. And there you go. And then we could copy, paste, and do the same for our drag. Here. Edit this. And our Y values will be our drag. Now for my professor grading this, I have timestamps in the video, so I know this is taking a while, but feel free to use the timestamps. Right here. CD right there. There we go. And then we could also do the same for CL over CD. We're just gonna have to make it here. CL over CD. And this will be equal to CL divided by CD. Right here. And then down here, we change our data. Yep. And there we go. That's basically it. Of course, there's more data we could collect from here, not just these plots. We could also do a CL over CD, like in one plot, like CD in the x-axis. There we go, like that. And yeah, that's basically it. It's pretty much everything. And yeah, thank you so much for watching, and I'll see you later.